November 18, 1944. Metz, France. 3:42 p.m. The ancient fortress walls of Fort Driant had withstood sieges for over a century when the first 155mm shell struck its reinforced concrete casemate with the force of a localized earthquake. German defenders who had laughed at American attempts to breach their position with smaller caliber weapons now scrambled through collapsing tunnels as subsequent rounds systematically dismantled defenses that Hermann Göring himself had declared impregnable. What they could not know was that the weapon destroying their fortress in mere hours had been designed by a team led by a former civil engineer who had spent the previous decade building bridges in Pennsylvania, and that the mathematics governing each precisely calculated trajectory would rewrite the entire doctrine of siege warfare. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. The fortress complex at Metz represented the culmination of centuries of military engineering. Originally constructed by the French in the 1870s following their defeat in the Franco-Prussian War, these positions had been reinforced by the Germans during their occupation, then reinforced again after they recaptured the city in 1940. Fort Driant alone featured walls of reinforced concrete measuring up to 3 meters thick in critical sections, with interlocking fields of fire, subterranean ammunition storage, and defensive positions designed to survive direct hits from contemporary artillery. The German High Command considered these fortifications among their most reliable defensive positions on the entire Western Front. The statistical impossibility of what was occurring defied every established principle of fortification warfare. Traditional doctrine held that reducing a modern fortress required either months of sustained bombardment, prohibitively close-range direct fire from tank destroyers, or costly infantry assaults through prepared killing zones. The 155mm howitzer shells now raining down on Fort Driant were striking from distances exceeding 12 kilometers, far beyond the range where defenders could effectively return fire. Each shell delivered 95 pounds of high explosive with sufficient force to penetrate the thick concrete and detonate within the casemates themselves. The mathematical precision required to consistently strike specific sections of a fortified complex from such distances, accounting for wind drift, temperature variations, barometric pressure, and the Coriolis effect, exceeded what most military theorists considered achievable under combat conditions. The broader strategic situation made the effectiveness of these weapons even more remarkable. By November 1944, General George S. Patton's Third Army had advanced rapidly across France following the breakout from Normandy, but now faced a critical obstacle. The fortress city of Metz guarded the approaches to the German border and the Saar industrial region beyond. The Germans had garrisoned the city with the 462nd Volksgrenadier Division, reinforced elements of the 17th SS Panzergrenadier Division, and fortress troops specifically trained in defensive operations. Approximately 40,000 German soldiers occupied prepared positions within a ring of interconnected forts, each supporting the others with overlapping fields of observation and fire. American commanders faced a dilemma that had plagued attackers throughout military history. Bypassing Metz would leave a substantial enemy force threatening supply lines and communications. Assaulting the fortresses directly would result in casualties that might cripple offensive operations for months. The Germans understood this calculation perfectly and had based their entire defensive strategy on the assumption that Metz would delay the American advance long enough for winter weather and supply difficulties to halt Patton's momentum entirely. They had not accounted for the specific capabilities of the weapon system now being employed against them with devastating precision. The vulnerability that would prove decisive existed not in the physical structure of the fortifications themselves, but in the doctrinal assumptions underlying their defense. German engineers had designed Fort Driant and its companion positions to resist artillery fire based on the capabilities of weapons available in the 1930s. The heaviest guns likely to be brought against them were the French 155mm Grande Puissance Fallu, or captured examples of similar weapons with maximum effective ranges of approximately 11 kilometers and shells that could penetrate perhaps 2 meters of reinforced concrete under ideal circumstances. The fortifications had been constructed to withstand such bombardment indefinitely, with ammunition and supplies stored in chambers protected by multiple layers of concrete and earth. What the German defenders failed to anticipate was the development of artillery ammunition with fundamentally different characteristics. The American M107 high-explosive projectile, weighing 95 pounds and measuring just over 6 inches in diameter, incorporated design principles derived from armor-piercing shells. Rather than simply exploding on contact with reinforced concrete, the M107 featured a hardened steel casing and a base detonating fuse that allowed the shell to penetrate deeply into concrete before exploding. The resulting detonation occurred within the structure itself, creating a combination of blast overpressure and fragmentation that was exponentially more destructive than surface explosions. Additionally, the M1 Long Tom and M2 gun motor carriage variants of the 155mm could deliver these shells at ranges approaching 14 kilometers with accuracy that earlier generation weapons could not match. The man who would orchestrate the systematic destruction of Metz's fortifications came from circumstances that suggested nothing of his future role in redefining siege warfare. Colonel William Harrison Morrison was born on March 15, 1902, in Harrisburg, Pennsylvania, to a family with no military tradition whatsoever. His father operated a small construction firm specializing in residential buildings, while his mother taught mathematics at the local high school. Young William demonstrated exceptional aptitude for mathematics and spatial reasoning, earning a scholarship to Pennsylvania State University where he studied civil engineering with a focus on structural mechanics and load-bearing calculations. Morrison graduated in 1924 during the post-war economic boom and immediately found employment with the Pennsylvania Department of Transportation. His work involved designing and overseeing construction of highway bridges across the state's challenging terrain. Over the following 15 years, he developed a reputation for innovative approaches to structural problems and an almost intuitive understanding of how forces distributed through complex geometric frameworks. Colleagues later recalled that Morrison could examine blueprints for a proposed bridge and identify potential weak points that computational methods would only reveal after extensive analysis. He published several technical papers on reinforced concrete construction and served as a consulting engineer on projects throughout the Mid-Atlantic region. The outbreak of war in Europe initially seemed distant from Morrison's world of construction projects and engineering calculations. He had married his college sweetheart, Margaret Hendricks, in 1927, and they had 3 children by 1940. At 38 years old with substantial professional responsibilities and a young family, Morrison had every reason to expect that military service would not disrupt his established career. However, the attack on Pearl Harbor and America's entry into the war changed everything. Morrison's expertise in structural engineering made him a valuable asset, and in March 1942, he received a commission as a captain in the Army Corps of Engineers. His initial assignment involved overseeing construction of training facilities and defensive installations along the East Coast. The work utilized his engineering background but offered little indication of his future role in combat operations. Morrison's methodical approach and ability to solve complex logistical problems impressed his superiors, and by late 1942, he had been promoted to major and assigned to the Ordnance Department's Artillery Development Section. This transfer would prove pivotal, placing Morrison in a position where his unique combination of skills in structural engineering and mathematical analysis could be applied to a problem the military had been struggling with for decades. The challenge facing American artillery planners in 1943 centered on the question of how to effectively engage hardened defensive positions without requiring prohibitively close approaches or extended bombardments. The experiences of World War I had demonstrated that even sustained artillery fire often failed to neutralize well-constructed fortifications. The massive concrete bunkers of the Maginot Line and similar defensive works represented evolved versions of those earlier positions, incorporating lessons learned from decades of military engineering development. American planners recognized that they would eventually face such positions in both the European and Pacific theaters, and existing weapons offered no satisfactory solution. Morrison approached the problem from a structural engineer's perspective rather than a traditional military viewpoint. He began by analyzing the actual composition and construction methods of modern fortifications, obtaining intelligence reports on German and French defensive works. What he discovered was that while these structures featured impressive surface protection, their internal architecture created specific vulnerabilities that could be exploited by weapons designed to penetrate before detonating. The key insight involved understanding how shock waves propagated through reinforced concrete and how explosive force could be channeled to maximize internal damage while minimizing the energy wasted on surface cratering. Working with ordnance specialists and metallurgists, Morrison helped develop modifications to the standard M107 projectile that enhanced its penetration characteristics. The shell casing was manufactured using higher quality steel with improved hardness characteristics. The internal explosive charge was reformulated to provide maximum blast effect within confined spaces. Most critically, Morrison developed firing tables that allowed artillery crews to calculate precise trajectories for engaging specific portions of fortified structures. His mathematical models accounted for dozens of variables that had previously been treated as approximations, resulting in accuracy levels that exceeded what experienced artillerymen considered achievable. By early 1944, Morrison had been promoted to lieutenant colonel and assigned to the European Theater of Operations as a technical advisor on artillery employment. His role involved training artillery units in the specialized techniques required for precision bombardment and coordinating with intelligence officers to identify optimal aiming points on fortified positions. The assignment brought him to England just as preparations for the Normandy invasion reached their final stages. While Morrison would not participate in the initial landings, his expertise would prove essential during the subsequent campaign to break out from the beachhead and advance across France. The 155mm howitzer that would become Morrison's instrument for revolutionizing siege warfare was not a new weapon. The M1 variant had entered service in 1942, combining a powerful gun with acceptable mobility for a weapon of its size. Towed by a heavy truck or tracked vehicle, the M1 could be positioned, in-placed, and prepared for firing in approximately 30 minutes under ideal conditions. The gun crew consisted of 11 men, each trained in specific tasks ranging from ammunition handling to firing computations. Under optimal circumstances, a skilled crew could sustain a rate of fire approaching 40 rounds per hour, though such rates could only be maintained for limited periods due to barrel heating and crew fatigue. The technical challenges of employing the 155mm howitzer for precision fire against fortifications exceeded those of normal artillery operations by several orders of magnitude. Standard artillery doctrine emphasized area bombardment, saturating a target zone with shells to suppress enemy forces or destroy unarmored equipment. Achieving consistent hits on specific structures required fundamentally different techniques. The gun had to be precisely surveyed and oriented using theodolites and other instruments normally associated with civil engineering rather than combat operations. Firing computations involved complex calculations that accounted for the specific ballistic characteristics of each individual gun barrel, variations in propellant temperature and composition, and meteorological conditions that changed throughout each firing mission. Morrison developed a systematic approach to fortress bombardment that transformed artillery employment from approximate fire into a form of long-range precision engagement. His method began with detailed photographic reconnaissance of the target, identifying specific vulnerable points such as ventilation openings, observation slits, and structural joints where walls met ceilings. Intelligence officers worked with Morrison to create detailed three-dimensional models of fortress complexes, allowing planners to visualize internal layouts and predict how explosive effects would propagate through interconnected chambers. Survey teams established precise coordinates for both gun positions and target structures using techniques borrowed from geodetic surveying. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. The firing process itself involved multiple stages of verification and adjustment. Initial ranging shots used specialized observation techniques to determine exact distances and establish baseline trajectories. Spotter aircraft equipped with radios provided real-time corrections, though Morrison preferred to use mathematical predictions based on precise measurements rather than relying primarily on observed adjustments. Each gun in a battery was individually calibrated, with firing data customized for its specific characteristics. Ammunition was inspected and sorted by lot number to ensure consistent performance. propellant charges were stored at controlled temperatures and loaded according to strict protocols that minimized variations between rounds. The results of Morrison's methodical approach became apparent during initial tests conducted at proving grounds in England during the spring of 1944. Artillery batteries employing his techniques achieved hit rates against fortified mock-ups that exceeded previous performance by factors of 3 to 5. Shells consistently struck within meters of their intended impact points at maximum range, and the enhanced penetration of the modified M107 projectiles allowed explosive force to reach chambers that had been considered safe from artillery fire. Senior officers who observed the demonstrations recognized that they were witnessing a fundamental change in the relationship between fortifications and artillery, though the full implications would only become clear under actual combat conditions. Morrison's philosophy regarding the employment of artillery reflected his engineering background and mathematical mindset. He viewed each bombardment mission as a problem in applied physics and structural mechanics rather than simply a question of firing the maximum number of shells in the general direction of the enemy. As he explained to battery commanders during training sessions, the objective was not to expend ammunition but to achieve specific physical effects with minimum expenditure of resources. A single shell striking precisely the right location could accomplish what hundreds of shells fired without proper calculation could not. This approach required patience, discipline, and trust in mathematical methods that many traditionally trained artillerymen found counterintuitive. The opportunity to demonstrate these principles under combat conditions arrived in November 1944 as Third Army operations stalled before the fortress city of Metz. General Patton, frustrated by the slow progress of infantry assaults against the fortified ring, sought alternatives that might break the stalemate without incurring unsustainable casualties. Morrison, now promoted to full colonel and serving as Third Army's senior artillery technical advisor, proposed a systematic bombardment campaign targeting specific fortifications in sequence. His plan called for concentrating available 155mm howitzers against individual forts, reducing them through precision fire before shifting to the next objective. The approach differed fundamentally from traditional siege tactics that dispersed fire across multiple targets simultaneously. Patton, known for his aggressive temperament and impatience with methodical approaches, surprised many observers by approving Morrison's plan without modification. The general recognized that frontal assaults against prepared fortifications would result in casualties reminiscent of World War I trench warfare, an outcome that would both fail to achieve his operational objectives and damage his reputation as a commander who achieved results through mobility and maneuver. Morrison's promise that precision artillery fire could reduce the fortresses in days rather than months aligned with Patton's need for rapid success, though the general remained skeptical that the actual results would match the predictions. Fort Driant became the test case for Morrison's theories precisely because it represented one of the most formidable positions in the Metz defensive complex. Located on high ground southwest of the city proper, the fort dominated approaches from multiple directions and housed a garrison of approximately 500 German soldiers. Previous American attempts to capture Fort Driant through infantry assault in September had failed with heavy casualties, reinforcing German confidence that their position was effectively impregnable. The fortress featured multiple levels of tunnels and chambers carved into solid rock, with reinforced concrete casemates protecting artillery pieces and machine gun positions. German engineers had spent years developing these defenses, incorporating lessons from both world wars and creating what they considered a perfect synthesis of natural terrain and modern fortification techniques. Morrison's bombardment plan for Fort Driant reflected months of preparation and analysis. Intelligence officers had compiled detailed information about the fortress from French resistance sources, captured German engineers, and aerial photography. Morrison personally reviewed this information, identifying 12 critical structural points where concentrated fire would likely cause cascading failures throughout the defensive system. These included ventilation shafts that could be collapsed to create carbon monoxide accumulation from the Germans' own defensive fires, structural support columns that bore the weight of multiple levels, ammunition storage areas where secondary explosions would magnify the effect of artillery strikes, and command bunkers whose destruction would sever coordination between defensive positions. The artillery concentration assembled for the bombardment of Fort Bryant represented the largest employment of 155mm howitzers against a single target in the European theater to that point. Morrison coordinated 8 separate batteries, totaling 32 guns, positioning them at carefully surveyed locations that optimized range, trajectory angles, and mutual support. Additional batteries of 105mm and 4.2-inch mortars were assigned supporting roles, providing smoke and harassment fire to prevent German observation of American preparations. The entire effort involved over 1,500 personnel when gun crews, ammunition handlers, surveyors, and support elements were included. Ammunition supply represented a significant challenge. Morrison's fire plan called for approximately 4,000 rounds of 155mm ammunition over a 3-day period, along with specialized fusing and propellant charges that were not part of standard issue. Ordnance officers had to coordinate deliveries from depots across the theater, prioritizing Morrison's requirements over competing demands from other units. The logistics involved were substantial, requiring dozens of trucks and careful scheduling to ensure that adequate ammunition reserves remained available at forward positions. Third Army's Chief of Staff personally intervened on several occasions to resolve supply conflicts, underscoring the importance that senior leadership placed on the Fort Bryant operation. The preparatory phase consumed 2 full days as survey teams established precise coordinates and gun crews placed their weapons according to Morrison's specifications. Each howitzer was positioned on carefully leveled firing platforms, with drainage channels to prevent recoil from shifting the gun position after repeated firing. Ammunition was sorted by lot and stored in temperature-controlled conditions as much as field circumstances allowed. Fire direction centers established communications networks linking forward observers, meteorological stations, and the gun batteries themselves. Morrison personally inspected each position, checking calculations and reviewing procedures with battery commanders who would execute his fire plan. German defenders observed the American preparations with growing concern. Aerial reconnaissance and forward observers reported the concentration of heavy artillery, though German intelligence officers initially assumed this represented normal support for a renewed infantry assault. The possibility that the Americans might reduce the fortress through artillery fire alone seemed implausible based on previous experience and established military doctrine. German commanders reinforced Fort Bryant's garrison, bringing ammunition reserves to maximum capacity and preparing for what they anticipated would be another costly but ultimately unsuccessful American ground attack. November 18, 1944, dawned cold and overcast, with low clouds limiting visibility but not precluding artillery operations. Morrison established his command post in a requisition farmhouse approximately 3 kilometers behind the gun line, close enough to respond quickly to developments but protected from German counter-battery fire. The command post featured detailed maps, scale models of Fort Bryant, and communications equipment linking Morrison to every element of his artillery command. Staff officers monitored weather conditions, computed firing adjustments, and maintained logs that would document every round fired during the operation. At 3:30 p.m., Morrison gave the order to commence firing. The decision to begin the bombardment in mid-afternoon rather than dawn reflected calculations about optimal lighting conditions for spotter aircraft and the desire to exploit specific tactical advantages related to the angle of the late autumn sun. The first salvo consisted of 4 rounds from different batteries, aimed at widely separated portions of the fortress to assess accuracy and establish baseline corrections. Morrison watched through binoculars as the shells impacted, noting the precise timing between muzzle flash and distant explosion that confirmed the extreme range of the engagement. The ranging shots struck within acceptable parameters of their intended targets, validating the survey work and firing calculations that had consumed the previous 2 days. Morrison authorized the commencement of systematic bombardment, and the character of the operation changed dramatically. Rather than sporadic fire from individual guns, batteries now engaged in carefully coordinated sequences calculated to maximize cumulative effects. Shells struck the same structural elements in rapid succession, each impact weakening the concrete and creating fractures that subsequent rounds exploited. The precise timing between rounds prevented defenders from conducting repairs or shoring up damaged sections between impacts. Inside Fort Dryant, the experience of the German garrison transformed from confident defense to desperate survival in a matter of hours. The first indication that something fundamentally different was occurring came when shells began penetrating deep into the fortress before detonating rather than simply cratering the surface concrete. Explosions within the enclosed spaces created overpressure effects that ruptured eardrums and caused hemorrhaging even among soldiers not directly exposed to shrapnel. Dust and pulverized concrete filled the air, reducing visibility to near zero and making breathing difficult. The systematic nature of the bombardment meant that as soon as defenders cleared one collapsed section, additional shells struck nearby positions, creating a cascading series of failures throughout the defensive complex. The ventilation system that German engineers had designed to maintain breathable air throughout the fortress became a liability under Morrison's bombardment. Shells striking ventilation shafts collapsed the structures and blocked airflow, while explosive gases from detonations were drawn through intact sections of the system, spreading toxic fumes to chambers far from the actual impact points. German soldiers attempting to man defensive positions found themselves forced to choose between suffocation in sealed chambers or exposure to ongoing bombardment in surface casemates. Medical personnel struggled to treat casualties in chambers that were themselves targets of systematic fire, with underground hospitals subjected to the same precise bombardment as combat positions. Communication systems within the fortress failed within the first 2 hours of bombardment. Telephone lines connecting different sections of the defensive complex were severed by explosions or buried under collapsed concrete. Radio communication proved sporadic at best, with the thick walls that had provided protection now preventing effective transmission of signals. The fortress commander found himself unable to assess the overall situation or coordinate defensive measures effectively. Reports that did reach his command bunker painted a picture of progressive collapse and mounting casualties, with no indication that American fire was slackening or that the bombardment would end before the fortress ceased to exist as a functional defensive position. Morrison monitored the operation from his command post with the detached precision of an engineer evaluating a complex project. Staff officers provided regular updates on ammunition expenditure, barrel temperatures, and minor mechanical issues affecting individual guns. Spotter aircraft reported observed damage, confirming that structural failures were occurring according to Morrison's predictions. The colonel made small adjustments to targeting as the bombardment progressed, shifting fire to exploit weaknesses as they developed and following a predetermined sequence designed to methodically dismantle the fortress from multiple directions simultaneously. By nightfall on November 18, Fort Dryant had received over 800 155mm rounds, each precisely aimed and most striking within meters of their intended impact points. German casualties exceeded 100 killed and twice that number wounded, though accurate accounting proved impossible in the chaos of continuing bombardment. Multiple sections of the fortress had collapsed entirely, burying equipment and blocking passages that connected different defensive zones. The garrison commander attempted to report his situation to higher headquarters but could only transmit fragmentary messages that conveyed desperation without providing clear tactical assessment. German officers at corps level initially dismissed these reports as exaggerated, unable to accept that artillery fire alone could reduce a modern fortress to such dire condition in mere hours. The systematic destruction continued through the night, with Morrison maintaining a reduced rate of fire designed to prevent German repair efforts while conserving ammunition for the following day's operations. Illumination rounds fired at irregular intervals prevented defenders from attempting evacuation or reinforcement under cover of darkness. The psychological effect of the nighttime bombardment proved as significant as the physical damage, with German soldiers realizing that the Americans possessed both the ammunition reserves and the technical capability to sustain precision fire indefinitely. Sleep became impossible in the fortress, with even soldiers not directly threatened by ongoing fire too traumatized by the day's experiences to rest effectively. November 19 brought renewed bombardment at even greater intensity as Morrison concentrated fire on sections of the fortress that remained partially intact. Intelligence reports based on prisoner interrogations and intercepted radio traffic indicated that German morale was collapsing rapidly, though the garrison commander continued to reject surrender demands. Morrison responded by intensifying fire against command bunkers and the specific chambers where senior officers were believed to be located. The targeting reflected both tactical calculation and psychological warfare, demonstrating to German defenders that nowhere in the fortress offered genuine safety from the precisely aimed American shells. Colonel William Harrison Morrison possessed a worldview that separated him fundamentally from the traditional military officers surrounding him in the European theater of operations. While career soldiers viewed warfare through the lens of doctrine, tactics, and historical precedent, Morrison approached combat as an engineering problem requiring systematic analysis and precise execution. His philosophy emerged not from military academies or combat experience, but from 2 decades of solving structural challenges in civilian construction where miscalculation meant bridge collapses and loss of life. He carried this burden of precision into military service, understanding that errors in artillery calculations would kill American soldiers assaulting positions that should have been neutralized. Morrison articulated his approach during a staff meeting in October 1944, weeks before the Metz operation commenced. General Walton Walker, commanding XX Corps under Patton's Third Army, had expressed frustration with the slow progress against German fortifications. Traditional artillery bombardments consumed vast quantities of ammunition while achieving minimal tangible results against reinforced concrete positions. Infantry assaults resulted in prohibitive casualties. Walker demanded solutions, and Morrison provided an answer that initially seemed almost absurdly simple. "The problem is not that our weapons lack sufficient power," Morrison explained. "The problem is that we employ them without understanding the specific vulnerabilities we are attempting to exploit. A fortress is not a monolithic structure but a complex system of interdependent components. Identify the critical structural elements, apply force precisely to those points, and the entire system fails regardless of how thick the walls may be." This structural systems approach to fortress warfare represented a radical departure from conventional military thinking. Traditional siege doctrine emphasized attrition, gradually wearing down defensive positions through sustained fire and accepting that reduction of hardened fortifications required time measured in weeks or months. Morrison rejected this framework entirely. Time itself was a resource that American forces could not afford to squander. Every day spent besieging Metz allowed German forces to consolidate positions elsewhere, extend defensive preparations along the Rhine, and potentially shift reserves to threaten American supply lines. Morrison argued that rapid reduction of fortifications through precision engagement served strategic objectives far beyond the immediate tactical situation. The mathematical precision Morrison demanded from his artillery batteries reflected his engineering background and his understanding that warfare, despite its chaos and violence, ultimately operated according to physical laws. A shell following a ballistic trajectory moved through space according to equations that could be calculated with extreme accuracy if sufficient variables were measured and accounted for. Wind speed and direction at multiple altitudes, air temperature and density, the rotation of the Earth itself, all these factors influenced where a projectile would strike. Traditional artillery practice treated many of these variables as approximations, accepting a degree of imprecision as inevitable. Morrison insisted that modern survey equipment and computational methods allowed elimination of most uncertainty, transforming artillery from an area weapon into a precision instrument. His subordinates initially resisted this philosophy, arguing that combat conditions precluded the careful measurements and calculations Morrison required. Artillery officers trained in rapid-fire missions found Morrison's methodical approach frustratingly slow and excessively complicated. The colonel addressed these objections by pointing to results from controlled tests conducted in England. Batteries employing his techniques achieved hit rates 3 to 5 times higher than conventional methods while expending substantially less ammunition. A single well-placed round accomplished more than dozens of shells fired without proper calculation. Morrison's approach required more time for preparation, but once firing commenced, it achieved objectives in hours rather than days. The resistance Morrison encountered extended beyond technical objections to his methods. He represented an outsider entering a professional military community with established traditions and hierarchies. Career artillery officers who had spent decades mastering their craft found themselves receiving instruction from a civil engineer who had worn a uniform for less than 3 years. Morrison's rapid promotion from captain to colonel in just over 2 years generated resentment among officers who had advanced more slowly through traditional career paths. His direct access to senior commanders like Patton, based on his technical expertise rather than command experience, violated informal protocols about how influence should be distributed within military organizations. Morrison navigated these tensions through a combination of demonstrated competence and careful respect for military customs he was still learning. He never claimed expertise in infantry tactics, logistics, or the broader operational questions that occupied most staff officers. His domain was the specific technical problem of employing artillery against fortified positions, and within that narrow field, he insisted on absolute authority. When battery commanders questioned his firing solutions, Morrison would walk them through the mathematical derivations step by step, showing how each calculation emerged from measured physical conditions. He converted skeptics not through force of personality but through irrefutable demonstration that his methods worked. The philosophical foundation underlying Morrison's technical approach rested on a belief that modern warfare rewarded systematic thinking over traditional martial virtues. Courage remained essential, as American soldiers would still face enemy fire regardless of how well artillery prepared their objectives. However, courage alone could not overcome concrete and steel. Intelligence and careful planning could achieve what bravery could not, reducing fortifications that would otherwise cost thousands of lives to capture through direct assault. Morrison viewed his role as providing American infantry with advantages that would allow their courage to be employed effectively rather than wasted against impregnable positions. This utilitarian perspective sometimes put Morrison at odds with officers who maintained more romantic views of warfare. He expressed no interest in the glory of battle or the honor of facing the enemy on equal terms. His objective was to create maximum inequality, to arrange circumstances so that American forces engaged German defenders under conditions of overwhelming advantage. If this meant destroying fortress garrisons from distances where they could not effectively return fire, Morrison considered that an optimal outcome rather than somehow unsporting. The faster and more completely German positions could be neutralized, the sooner American soldiers could advance with acceptable risk. Morrison's correspondence with his wife Margaret during this period revealed a man struggling with the moral weight of his work even as he pursued it with relentless determination. In a letter dated November 10, 1944, he wrote that he found himself calculating the structural failure points of buildings with the same detached precision he had once applied to ensuring bridges remained standing. The realization troubled him. He understood that his targeting recommendations would kill German soldiers, yet he approached the work as a technical problem divorced from its human consequences. Morrison acknowledged this compartmentalization as perhaps necessary for maintaining the focus required to execute his duties effectively, but worried about what it revealed regarding his own character. Margaret's responses, preserved in Morrison's personal papers, provided both emotional support and moral grounding. She reminded her husband that his work ultimately served to protect American soldiers and accelerate the defeat of a regime responsible for unprecedented atrocities. The German soldiers defending Metz had chosen to serve Hitler's government and bore responsibility for that choice. Morrison's artillery might kill them, but it would also prevent them from killing Americans and spare civilian populations from prolonged combat in their cities. Margaret encouraged her husband to maintain the perspective that his engineering precision, far from being cold or inhumane, actually minimized total suffering by ending battles quickly rather than allowing them to drag on with mounting casualties on all sides. This moral framework allowed Morrison to pursue his work with the intensity it required while maintaining his sense of himself as fundamentally a builder rather than a destroyer. He viewed the reduction of German fortifications as analogous to demolishing a condemned building, a necessary preliminary step before reconstruction could begin. The faster German defensive capabilities were eliminated, the sooner the war would end and the work of rebuilding Europe could commence. Morrison looked forward to that reconstruction phase, imagining himself eventually applying his engineering skills to peaceful purposes once victory was achieved. The systematic nature of Morrison's approach to fortress warfare extended beyond firing calculations to encompass every aspect of artillery operations. He insisted on standardized procedures for ammunition handling, storage, and preparation. Shells were inspected individually for defects that might affect flight characteristics. Propellant charges were measured precisely rather than simply loaded according to standard specifications. Gun crews received instruction not just in operating their weapons but in understanding the physics underlying artillery fire. Morrison believed that artillerymen who comprehended why particular procedures mattered would execute those procedures more carefully than soldiers simply following orders without understanding their purpose. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.